Upon completion of this lesson, students should be able to describe the various wired ICS protocols, describe some of the features that distinguishes one protocol from the others, describe ICS network protocol frames and structures. Industrial control system protocols range from wired to wireless. Wired protocols include Ethernet Industrial Protocol, Ethernet IP, Common Industrial Protocol, CIP, Modbus, Modbus Transmission Control Protocol, Modbus TCP, Distributed Network Protocol version 3, DNP3, Process Field Bus, Profibus, DeviceNet, Controller Area Network, and Ethernet for Control Automation Technology, EtherCAT. With an ever-increasing risk that ISCs are being subjected to, it is imperative that cybersecurity professionals gain a good understanding of the communication protocols with which these systems operate and the threats that exist in securing them. DNP3 is a protocol standard that is used to define communications between remote terminal units, RTUs, master stations, and intelligent electronic devices, IEDs. It was originally a proprietary model developed by Harris Controls Division and designed for supervisory control and data acquisition, SCADA systems. DNP3 is a master-slave control system protocol and is accepted standard by the electric, oil and gas, wastewater, and security industries. There are numerous system architectural configurations for DNP3. A typical multi-drop configuration that includes one master station and multiple outstation devices is shown in the figure. DNP3 is a 4-layer subset of the OSI 7-layer model. The layers are the application, data link, physical, and pseudo-transport layers. The pseudo-transport layers include routing, flow control of data packets, and transport functions such as error correction and assembly, disassembly of packets. The data link header contains 2 start bits, 0 by 0564, that help the receiver determine where the frame begins. The length specifies the number of octets of the remainder of the frame, excluding the cyclical redundancy check, CRC section. The data link control octet is used for the sending and receiving link layers for coordination. The data link frame of DNP3 is shown below. The 2-octet destination address specifies which DNP3 device should process the data, and the 2-byte source address identifies the DNP3 device sender. With the 2-byte addressing scheme, there are over 65,500 available addresses in which every DNP3 device is required to have a unique address for sending and receiving messages to and from each other. 3 destination addresses are reserved for DNP3 as broadcast addresses. The data payload is divided into blocks, with each block containing a pair of CRC octets for every 16 data octets, except for the last block. Note that the data link layer can only handle a maximum of 250 data octets. The application layer fragments a message depending on the receiver's buffer size, which ranges from 2048 to 4096 bytes. Consequently, a fragment of size 2048 must be broken into 9 frames by the transport layer before passing on to the data link layer. Modbus is a proprietary serial communications protocol originally published by Modicon, now Schneider Electric. It is used with programmable logic controllers, PLCs. Modbus, the most widely deployed ICS protocol, is an application layer messaging protocol. Transactions can either be a query response type, where only a single slave is addressed, or a broadcast no response type, where all slaves are addressed. The 3 major implementations of Modbus include Modbus Plus, a high-speed token passing network, asynchronous serial communication, and Modbus TCP, a TCP IP over Ethernet encapsulation. The Modbus protocol specifies the protocol data unit, PDU, which is comprised of the function code and the data field, and is independent of the underlying communication layers. A summary of the most important function codes is shown in the table. The IEC 60870.5 is an open standard for the transmission of SCADA telemetry control and data. Of particular interest in this module is the IEC 60870-5-104, a companion standard which defines the transport controls and data of the SCADA system over TCP/IP networks. A portion of the generic protocol frame structure of the IEC 60870-5-104 companion standard is named as the Application Protocol Data Unit, APDU, is shown in the figure below. The Application Protocol Information, APCI, is comprised of the first 6 octets, and the remainder of the APDU contains the Application Service Data Unit, ASDU. The APCI control field can be either one of the following types: information, supervisory, or unnumbered. These are all very similar to the control fields used in high-level data link control, HDLC, a synchronous data link layer protocol developed by the International Organization for Standardization. The ASDU structure includes the data unit identifier and the data payload of one or more information objects. The data unit identifier defines the specific type of data. The address determines the identity of data and the cause of transmission, COT. The control field structure for the information type is shown in the field below. The two least significant bits indicate the type of APCI control field, i.e. 10 for supervisory, 11 for unnumbered, and 0 for information. The 8-bit wide code types shown in the table below identify some of the 58 groups that are currently defined. Furthermore, information code references defined in IEC 60870-5-104 are provided in the ASDU. For instance, code type number 9 has reference code M_ME_NA_1, indicating measured value, normalized value. Just like Modbus TCP is typed to a specific port, 504, IEC 60870-5-104 is assigned TCP port 2404. Thus, deciphering and identifying ICS packets, at least for these two ports, would be much easier by focusing on the port numbers that are being used for communication. Common Industrial Protocol, CIP, is a unified communication architecture used throughout the manufacturing enterprise. Two well-known network protocols developed by Rockwell Automation that are based on CIP are the device net and the control net protocols. These two network protocols are now owned and maintained by Open Device Net Vendors Association, ODVA, and the Control Net International. These two organizations have worked together in developing the newest member of the CIP family, the Ethernet Industrial Protocol, Ethernet IP. Having a common application layer, device net, control net, and Ethernet IP enable maximum interoperability among devices from multiple vendors by sharing an object library and device profiles. These result in faster startups, superior diagnostics, and plug-and-play capability. Furthermore, Ethernet IP provides both explicit information and explicit control messaging services that are essential in control and device level networks. Ethernet Industrial Protocol, Ethernet IP, a member of the Common Industrial Protocol, CIP, provides the network tools to deploy standard Ethernet technology to enable industrial automation applications and enterprise connectivity for data and control. This protocol runs over TCP/IP or UDP/IP. TCP/IP uses the reserved port 0xAF12 44818 for transmitting explicit messages, while UDP/IP uses the reserved port 0x08AE 2222 for transmitting I/O messages. The typical Ethernet frame with the encapsulated Ethernet IP data and the encapsulated packet format are shown in the figures. The 2-octet command, CMD field, represents various types of commands such as broadcast, session opening and closing, and receiving and sending data for connected and unconnected messaging. The 2-octet length information represents the length of bytes of the data portion of the encapsulation message. The total length of the message is the sum of the number in this field plus 24 bytes for the encapsulation header. The 4-octet session handle represents the session identification and is application dependent. The status code, a 4-octet value, indicates whether the receiver is able to execute the requested encapsulation command. It is initialized to 0, indicating a successful execution. The sender of a CIP command may place any value in the 8-octet sender content field of the header, and the receiver will return the same value without modification in its reply. The last 4 octets are set by the sender to 0 and verified by the receiver. If this field is non-zero, the receiver will discard the encapsulated packet. The encapsulation data, which can take a maximum size of 65,511 bytes, follows the header. EtherCAT is a real-time Ethernet technology from Beckhoff. It is a proprietary field bus protocol system that can deliver as much as 1,000 distributed input-output I/O operations in 30 microseconds on an almost unlimited network size. EtherCAT was standardized in 2005 as IEC PAS 62407 and is now integrated in a number of other standards, IEC 61158 and IEC 61784-2. The fundamental principle of EtherCAT is referred to as pass-through reading. In this scheme, messages are delivered according to some sorted preference, and replies are collected in the reverse or loop-back fashion. The EtherCAT frame fits nicely into the Ethernet frame by simply replacing the entire IP packet as shown in the figure on the next slide. The EtherCAT starts with the standard header comprised of a 2-byte information on the length of the header, a reserve bit, and another 2-byte information on the message type. After the header comes the process data objects, PDOs. The PDOs, which are individually addressed for each node in the network, correspond to the number of nodes and messages within the frame. Each PDO contains data for a specific node. The last item in the frame is the working counter, WC. This works the same way as a frame check sequence, FCS. The EtherCAT frame fits nicely into the Ethernet frame by simply replacing the IP packet as shown in the figure. The EtherCAT frame starts with the standard header comprised of a 2-byte information on the length of the header, a reserve bit, and another 2-byte information on the message type. After the header comes the process data objects, PDOs. The PDOs, which are individually addressed for each node in the network, correspond to the number of nodes and messages within the frame. Each PDO contains data for a specific node. The last item in the frame is the working counter, WC. The way EtherCAT processes and delivers the messages has significant advantage over Ethernet. However, certain devices may encounter difficulty in handling the speed of the message delivery. In this case, EtherCAT may be configured to slow down at a rate with which the device can operate properly. Additional advantages of EtherCAT are flexible topology and precise synchronization, which is critical in process control. Process Field Bus, Profibus, is an open field bus serial network standard and is mainly used for real-time control applications. The protocol operates on the application, data link, and physical layers of the OSI model. Profibus comes in three forms: Profibus Process Automation, PA, Decentralized Peripherals, DP, and Profibus Fieldbus Message Specifications, FMS. The Profibus DP telegram header, 11 bytes, and data field, variable length maximum of 244 bytes, are depicted in the figure. The header consists of the starter delimiter, SD, the network data length, LE, the length repeated, LER, destination address, DA, source address, SA, function code, FC, the destination source access point, DSAP, the source service access point, SSAP, the frame checking sequence, FSC, and the end delimiter, ED. ControlNet is a token passing bus control network protocol that is based on the IEEE 802.4 standard. The nodes in the token bus network are configured in a ring topology, and in particular, in ControlNet, each node knows the address of the preceding and the succeeding nodes. The ControlNet protocol became a part of the Common Industrial Protocol, CIP, family protocols in 1997. The Median Access Control, MAC, frame format transmitted on the ControlNet is shown in the figure. The transmitted data, which could be as many as 510 bytes, is carried by a series of link packets, L packets. A link packet can either be a fixed tag or a generic tag. The fixed tag L packets are used for unconnected messaging and network administration, while the generic L tags are used for connected messaging.